Okay, thanks for having me here today. My name is Will Foster. I work at Red Hat on the performance and scale engineering side of the house. So my job is mostly kind of in the DevOps infrastructure area. Today I'm going to talk about a project called QUADS that myself and my other colleague built to solve some of the problems we have with mass provisioning of large sets of infrastructure and networks on demand. Oh, it's green, yeah. Okay. All right, so this isn't a very long talk, so I would just ask that if you have any questions, just keep them towards the end. And then after that, I'll be around the conference to talk to you guys about any of the things that we discuss here today. So let me get to it. So before you can kind of understand what the QUADS project is and kind of how we've automated large swaths of our infrastructure with Python and specifically automated our jobs with Python, I think it's good to give a car analogy as far as what my job is at Red Hat and kind of how we go about our everyday. And there's never been a car analogy on the internet when it comes to open source. So I'm going to be the first one that's ever going to do a car analogy. We all know that's not true. Car analogy. But basically, what I want you to consider is in kind of the performance and scale world, high performance servers, very large, powerful, cutting edge machines would be considered race cars. And extremely fast, low latency networks, 10 gig, 40 gig, 100 gig, would be sort of the race tracks that these race cars compete on. And the actual races would be performance and scale testing of various projects or open source products. It could be OpenStack, it could be Enterprise Linux, it could be Kubernetes, anything you think of. Those are sort of the car races. And then the people that drive the actual cars, we want to call them race car drivers. These are sort of the performance and scale engineers who their job is to try very hard to break things at scale and then figure out why they broke and then make improvements so when large businesses or large consumers use a particular open source product, they don't run into the same issues that we might hit in our R&D environments. And sort of the consensus around this kind of the goal is to schedule as many of these races on as many tracks as possible all at the same time and trying to avoid head-on collisions and explosions into fiery swaths of mayhem. So, sort of my job in facilitating this is I'm kind of the pit crew and the track engineer that helps people performance test all of these open source products at scale. And the QUADS project helps us automate all of this. All right, so the Reader's Digest, in case I lost you on that previous example of the car analogy, is very simple. I'm on a two-person team. We administrate about 400 large-scale performant bare metal servers, and we have 40 and 100 gig networks. And all of these systems facilitate any manner of product testing and performance and scale testing for any open source product, like just about everything. And our job is to basically make all this happen at the same time, automate all of it, and work on the automation. So we basically automated ourselves out of a job with Python and with a couple of the tools that I'm going to talk about. So just to field interest in kind of understanding here, who here has heard of the Foreman project? It's infrastructure, kind of a life cycle management. Okay, who's heard of OpenStack? Okay, awesome. So I'm going to make some references to both Foreman and to OpenStack in this talk, but none of those components are necessarily needed to use the same sort of automation workflow that we've developed and we continue to work on. So I have some sort of cookie cutter DevOps slides in here. I'm not going to really go into too much detail, but basically our team design is there's two of us. There's about 160, 170 core, what we would call performance and scale engineers. And then they work on different application stacks within Red Hat. So this might be OpenStack, OpenShift, Kubernetes, RHEL, JBoss, Ansible, you name it. So our job is kind of to build the tooling and build the automation for these groups and then operate these large internal environments so they can stress test and try to break their products. we keep all our stuff obviously in source code repositories. Our favorite RCM is Git. We do a lot of our automation around there. A lot of our CI is driven by this, and we try to take an effort to sit in on all the development sprints and all the development sort of sync ups of the various teams, so we know what's happening from a release perspective, as well as try to anticipate challenges. Like if, we know that JBoss is going to have a release next month, but we know that OpenStack is, month 5 out of their 6-month release cycle, we're going to have to juggle the resources that we have to make sure people have the right hardware to do their job. But basically, we just try to be excellent to each other. Just try to party on. So, on to QUADS. So what is QUADS? So QUADS stands for Quick and Dirty Scheduler. It does a little more than that, but I should start with what it isn't. So it's not an installer. It's not a provisioning system. It bridges a lot of sort of interchangeable pieces together, and it fits a need that we have that nothing was available out there in the upstream ecosystem. Some of the other things that's more important to me is that it solves problems that we don't want to solve. So, documentation is critical for any project. But if you have wrong documentation, that's almost as bad as not having any documentation. So one of the things that QUADS does for us is it keeps all of our internal infrastructure documentation up to date, but it also publishes what's currently happening within our R&D environments to the rest of the company and anyone that's interested. So if you're a development group and you want to know if there's hardware available, you can just go to this one page. It's automatically updated when the environment changes, and you don't have to ask anybody. There's no secret if 20 servers or so are available for you for, say, a couple of weeks. So we took this sort of mindset that we want to automate the boring stuff, and we want to save ourselves time to work on the things that truly matter and the things that are really critical to stay up to date and current with. So what exactly does QUADS do? So in a nutshell, it's a programmatic YAML-driven scheduling framework. We have large sets of machines and networks that are able to be scheduled at any point in the future against an unlimited schedule. So we use PyYAML for that. And we basically create and maintain a metadata structure that describes all of our network switches, all of the bare metal systems that we have, all of the VLAN configs, all the sort of sorted pieces of an infrastructure that you might have to track. We make those as metadata objects, and then each server has its own sort of class that describes it. And then within that, we're able to mash machines together, we're able to pull them apart, and we're able to do it in the future. So if we know there's going to be a big demand, say, for the Ansible group to make a new release, and they have to do some performance and scale testing before they release it at a large scale. Let's say they've seen a problem with 10,000 servers. After 10,000, Ansible Tower falls over, for example. Well, one of the things that we would accommodate for them is we would set a schedule 2 weeks in the future that at a certain time and a certain date, all of the machines that we've picked out for them will spin up, they will provision themselves. All the network switches will get their own individual VLANs. User accounts will be created on all the out-of-band interfaces, and then everything will be sort of published to that group for them to use for a defined period of time. So this is sort of how we use QUADS internally. Basically what I just talked about. One thing that's important here is we try to schedule as many parallel, isolated, what we would call assignments or cloud assignments, because we're not that creative, and everyone calls everything cloud nowadays, to run all at the same time and be as efficient as possible. There's always a carbon footprint. Electrical costs money, bandwidth costs money, idle systems are expensive. So one of the things we try to do is schedule as many future machines and sets of networks in advance back to back, so that at any point in time, all of the infrastructure is constantly doing something. And when it's not doing something, it powers itself off, and it announces that it's available to anyone who might need some infrastructure. Cool. So I like pictures. This is a good representation. It's a little old. It's from February of 2017. But what I want you to yield from this is sort of the level of efficiency that we're able to schedule and automate in the future. So all of these assignments, all of these sort of individual performance and scale workloads were scheduled in like the September timeframe. So that means when February comes around, and depending on the date, different subsets of the infrastructure spin up, they get reprovisioned, they get configured, they get passed over. And then when that period of time is done, it gets spun down and immediately handed to somebody else, and so forth. So this is a kind of a good representation of trying to be as efficient as possible with the hardware and the networks that are on the floor. Here's another example. You can see it's there's a lot going on there. It's pretty busy. So we have kind of the machine type breakdown. We have some correlation with a ticket tracking system. We happen to use RT. And a lot of this in last year was more OpenStack related, but we start to see a lot more of stuff within the company around containers and other workflows. But this is a pretty busy month, pretty busy couple months. And we didn't have to do anything to make all this happen. We just had to enter it into the QUADS scheduler, make sure nothing breaks hardware-wise, and then all this stuff just happens. And here's some of the sort of the scale results that we would expect to get from a performance and scale engineer perspective. This happens to be a Ceph workload. So these are some of the results we would derive from what we call the scale lab, which is where QUADS runs. Cool. So what are we solving here besides the stuff we've already talked about? Who's heard of server hugging? Has anyone heard of server hugging? Okay. Yes, server hugging. So you probably know what it is, but you might call it a different word. So server hugging is the idea that if you give someone something, like if you particularly give developers something, like a server, and say, this is just temporary, you can use it for a while. Well, the human tendency is to hold on to that as long as possible. Like, it's not technically yours. It might belong to your groups or your organizations, but like, it's yours. Okay, like that's your thing. All right, like that's server hugging. Okay, so one of the main goals for this was to try to eliminate server hugging, or at least to lessen it. But when you take something away from somebody, if I give you a server, and I say you have the server for a week, and then day 6 comes around, wait, but I need my server, my stuff is on there. So it's a social experiment, but at the same time, if you take something away from somebody by only letting people have things in short little spans of time, you have to give them something back. It's just push and pull. So what we give back is a level of transparency with what's actually happening in the infrastructure. Typically, especially in large companies, it's the case that if you're a developer and you work on, say, the product engineering group, there begins these little silos, these pockets of hardware that the company owns. And your ability to get resources as an engineer is directly related to how political your manager is to fight with the other managers to get a set of servers. And if your manager's not that good at it, then you're going to get old stuff. You might not get free cycles to run your gear. And there's going to always be more demand for resources than there are actual resources to give out to people. So this is what we sort of tried to solve here with the server hugging. And by publishing the schedules in advance, people can see what's being used for what. Obviously, there's an automation angle. Humans are going to make way more mistakes than systems normally. But one sort of glorious thing about automation is that when it does fail, it fails in catastrophic ways, right? Like, to sysadmin is to push the wrong config to one server, but to DevOps is to push the wrong config to 1,000 servers, right? When automation fails, it's in some glorious way that's some giant fireball, and it's kind of funny, but so that's the downside of automation. But we try to automate as much as possible, and this is sort of where we get the Skynet theme from. Because if we don't have a good harness on what is automated and what's actually breaking because of a lot of noise, we can just end up with spectacular failure and series of failures. Which again is kind of funny if you look at it from a pragmatic perspective. Cool. So maximizing idle machine cycles. We've already talked about this, but it's very important to not have systems and infrastructure sitting there running, not doing anything. That's wasted time. That's an opportunity. Someone else could have come in there and got their work done. So that's sort of another goal that we're trying to solve here. All right. So we want to be more like Airbnb and less like a hobo house. Okay, Airbnb has very structured guidelines. You can only stay in an Airbnb for 4 weeks maximum. We have a similar sort of reservation system within our scale lab. You generally know what you're going to get. Sometimes the pictures are misleading, but you generally can kind of expect the type of experience you're going to get. And you can't be a raging criminal and rent Airbnb, I hope, right? Hopefully there's some checking mechanism that makes sure that if you're some, evil villain from planet Neptune, that you can't come to Earth and just start a string of Airbnbs. I would hope. So those are sort of the guidelines that we have our lab open to. There's obviously some cost savings, so I did some very, very ugly envelope math as far as what we're saving from kind of a human hour perspective. This is going to assume that nothing is automated, right? Nowadays, in 2018, you're at least doing automated provisioning, say, for systems. You probably have templates, you're probably using Ansible or Puppet or Chef or something. If we didn't have any of that and we said, we're going to come straight from 1994, this is how long it would take to do stuff. We have some tremendous time savings from a 2-person team to get a set of machines. So this would be if 100 servers and switches and networks and VLANs changed hands, what it would take if we did everything manually in our environment. And it would take about 45 hours. It would take over a working week to hand out 100 machines. Each machine has its own switch configuration that corresponds to that. There's out-of-band passwords. There's validation that happens. Nobody wants to do that manually. So we're able to do all of this in the span of about 3 or 4 hours on Sundays when our scheduler kicks in and it goes out and it finds which machines are scheduled to be relinquished, which machines have to move to some other group, or which ones have to power down and go into the free pool. I kind of broke down, time-wise what it would take if you did it manually. I'm not going to bore you with it. But let's look at some more pictures. Okay, let's talk about how all of this works. I've kind of gone on and on about, why this is so cool and how it saves us time, but I want to show you kind of under the covers how it all works. So, I can tell you that my career in graphic design does not look promising looking at this, but it's a fairly simplified sort of architecture diagram. Who here has seen the movie Office Space? It's my favorite movies in the world. Okay, if you haven't seen it, you should go check it out. I even have an Office Space Bob's on my laptop. It's that important. Okay. So Office Space is like the opposite of a company you want to work for. So if you haven't seen that movie by Mike Judge, you should go watch it. So there's a typical engineer up here. We'll call him Milton. And he's going to use QUADS. So we expose a JSON API. It's basically a Python WSGI server with a CLI that works in tandem. This manipulates a YAML file on disk. We don't use a database yet. I'll get to why, and I'll get to why we should later. But we use PyYAML to basically create and maintain this sort of hierarchy of metadata that describes all the objects in our infrastructure. We can plug in our own provisioning backend. In this case, we use Foreman. I'm just a really big Foreman fan. I like their API. I think it's a great project. You could plug in something else besides this because, again, QUADS is not a provisioner. It is simply sort of a scheduler that has hooks to other pieces. Your provisioning, the muscle of it, is going to come from a hook called move hosts. That's where you would define what actually happens when you want to reprovision an environment or you want to go make a change to certain switches to make the current state look like the desired state. There's some stuff that happens on the back end with IPMI and out-of-band, and then there's this Wiki update portion that pulls in the current state of the environment and then updates the current documentation online as far as what are the machines that are available, who's using it, what are they using it for, links to graphs, links to other stuff, which we'll look at. And again, I want to drill down in here to the move host. This is the pluggable part that you can sort of define yourself. Currently, we only support Foreman, but we're working to also support Beaker, and I'm got another RFE in to basically make Ansible drive all of it. So, all right, cool. So move host, pretty simple. You just run this, and it will check if a machine is supposed to be in a different state than it is now, and it will take care of it. Okay, so this is, again, I'm not going to win any awards here with graphics design, but this is sort of our foreman workflow on the back end. This sort of, we remove certain roles. We add a couple roles with Foreman's Role-Based Access API. We make some IPMI changes. We first check if the temporary group or user that's using a set of machines exists on the IPMI and out-of-band interfaces, and if they do, cool. We set the password to match whatever we tell them the password is. If they don't exist, then we create it. Then there's a pretty exhaustive validation phase once this happens. There's also some switch work that happens. We go out to all the switches, depending on the VLAN design that they have specified. We support 2 right now. We will set that up for them. And then there's sort of some extensive validation that happens that we first make sure the systems are in their desired state, that there's a clean operating system on it, that it's reachable, that all the network faces are present. We then validate the network side to make sure that we can reach each of the interfaces depending on its current VLAN, what VLAN it should be in, that that's not wrong. And then lastly, we do some facts collection. There's a really cool project called Ansible CMDB, which it takes about 5 seconds. You run it against a machine or a set of machines, and it creates this very nice sort of breakdown of statistics about your machine using Ansible facts. So we collect that and carve up a page out of it. And then when all the validation passes, we get a message on IRC saying this new environment is here. Emails go out to the users. If any one of these steps fail, then we get alerted and it tells us what failed so we can drill in and fix that particular issue. And with hardware, you know, when you have a couple hundred servers, stuff's just going to fail all the time. I mean, it might be small, you might be able to protect against it, but having good monitoring and having good validation is important. A little bit about the internals. I'm not gonna go through all the stuff. You can look at this on your own. It's on GitHub. It's all documented. But this is an example of sort of the metadata structure that we would see per machine. So this machine, C08, H21, R630. We can see the current environment that it's supposed to be in, Cloud 02. We can see what's called the default environment. This is where the machine would go, or a set of machines would go when they don't have anything to do. This would be sort of our spare pool. And then we keep a historical record of all these sort of isolated assignments this machine has been a member of. All right, so on to some network stuff. We support 2 VLAN modes. One, basically, every interface, say it has 4 interfaces. Interface 1, across all the machines you have, is in its own VLAN. Interface 2, across all the machines, etc. We have another Q&Q mode. This is more for NFV type. I don't know if you guys are familiar with NFV. It's sort of a network function virtualization stuff. The demand there is to have all the interfaces in one layer 2 VLAN by itself. So those are the 2 modes we support. We're going to add more. And then this is something new. This should be in place in about a week. We take the last interface on every machine and we apply basically an RFC 1918 subnet or VLAN on top of that interface for things like floating IPs, or if you want to have a /24 or 23 inside of your corporate infrastructure that's publicly reachable, we will tag that onto the last interface of all your machines, and that's configurable. And then here's sort of a breakdown of how we would set this up by hardware type. We currently just have Dells and Supermicros. We have quite a few of them, but they each want to do things differently. So all of your custom VLAN stuff would happen on the network 4, and then network 1, 2, 3, and 4 would be purely up to the user or the engineering group to do whatever they want to do. We set up isolated VLANs for them just as a courtesy, and we lay down configs for those VLANs for the interfaces, but they can do whatever they want. And then there's the public sort of network that we would call the provisioning network. All right. I know I'm going through this fairly quickly, but I don't want to bore you either, but here's some more pictures. So this is how the dynamic documentation stuff works. We basically use Python to query Foreman, and we query a couple of other things within QUADS. We return a markdown, and then we push this markdown. Currently, we have it using WordPress, but it could be any sort of backend that supports markdown. It could be Pelican, it could be whatever, anything that supports markdown. And we constantly run this, and if there's a change in any of the infrastructure, it gets updated. Otherwise, it doesn't do anything. So here's an example of what it actually looks like. So this is what we would call sort of our racks page or our infrastructure documentation. This is going to be a list of all of the gear that we have available in, say, an environment that QUADS manages. I have the serial number published here, so these Dells are out of support. If you would like to pay for the support for these machines, these are the serial numbers here published. So I've got a comment before on a similar talk, and someone's like, but you got the serial numbers. And I'm like, well, if you'd like to pay for it, here it is. So here's the typical sort of information, MAC address, IP. Now, most of this is going to be static. MAC addresses really don't change. IPs might change. But if you look on the far right-hand corner, we have workload, and then we have owner. So that's dynamic, because that's going to constantly change. If you drill down a little more, this is what would be our summary page. You can actually get an overview of everything that's happening in the environment when it's happening. So this was taken, geez, I don't know, maybe a couple months ago. But we have basically the isolated assignments, or the working clouds here on the left, the number of machines, their purpose, what's actually happening right now, the owner of that environment, so who the contact person is. And then for OpenStack folks, there's an instack-env file that we auto-generate and keep up to date. OpenStack-env.json in the OpenStack world is for OOO and Ironic, that you feed this file. It's sort of like an infrastructure helper. You feed it to the OpenStack installer, and then OpenStack goes out and deploys based on what's in that JSON file. And then lastly, we have some Ansible facts that we collect, and then we do some other stuff with Dell, where we check if there's any change, like if the BIOS level stuff is set correctly. So here's you're drilling down inside a specific assignment, and then we see sort of when it's going to start, when it ended, the duration, how much time remaining. And again, this is all public facing within the company. So if you need some hardware to do something, you can easily look one place, you can see what's free, and you can see what's in use. Some other boring stuff, if we detect failures, we automatically pull them out of the pool, so we're not trying to deploy on faulty stuff. This is a very ugly PHP calendar we don't use, but we generate it anyway. This is surprisingly useful from a scheduling perspective. This looks like the Windows 95 like disk defrag utility. Do you remember that? It's like that giant ugly grid, and the little blue thing moves, and it doubles as a defragmentation and also a countdown to when your computer's going to crash in the Windows days. But what this shows, this is what we would call our heat map, is that we generate one of these. It's constantly updated, and it shows the month. And then on the left-hand side are all the machines that we have in the infrastructure, and on the right-hand side are sort of these diagrams or colors or blocks that show you what's being used for what. And if there's a tooltip, you hover over it, shows you the ticket number, the day of the month, what it does. If you zoom out, it's even more like the defrag utility, right? But it's useful. So you can look and sort of see, all right, the gray is unused. The gray means there's a spot here where machines are free for people. So, the different colors are going to be actively used environments. So I've found this is useful to look at. If you're colorblind, you probably want to get someone else to look at it for you, but it's pretty useful. So, at least from a scheduling perspective. All right, so we did mention Ansible CMDB. This is just an example of some of the info that it pulls. And you can drill in more, interfaces, memory used, number of interfaces, CPU, all that stuff. This is something we sort of custom put in there. This is only for Dell hardware, but this will scrape the out-of-band interfaces, and it will tell you using RackADM if the power optimization settings, what they are, and if they're not set to what you want them to be. So we see like, oh no, this one is not power optimized. Because again, these are performance scale workloads that we have. This sort of stuff's important to us. Real quick on CI, we don't do anything too revolutionary here. We use Jenkins, we use Garrett, and we use GitHub. And we just have some tests in there. We have a sandbox that goes in. It runs all the variations of the QUADS commands. We use Flake 8, and we use shell check for some of the shell glue that we have. And there's a voting system. So if you've ever used OpenStack or you're familiar with bigger projects, we try to copy what they do. There's a cool CI/CD sort of pipeline with packaging. We're using Copper, which is a Fedora infrastructure project that lets you automatically build RPMs when a certain branch in Git changes. So this is super useful that if we make a change to quads, your RPM repository will pick up the new version of the package, and then your package manager will pick it up, and it's easy to keep things up to date. So if you haven't seen Copper and you're doing RPM packaging, it's a really useful tool. All right, so let's get to some things that we want to change about this. So we are using a flat file architecture, which is not ideal for a lot of ways, or a lot of reasons. But it is easy to debug, it is easy to test, and it is easy to replicate. There's a lot of downsides. It's slow. System calls are quick, but they're not going to be as quick as having something in memory or in a database, typically. And we have to write a lot of conservative code when it comes to managing file handles and managing things like locking and not having race conditions and things like that. So we are going to move to more of an asynchronous architecture. Currently, we don't really care with our usage, because 2 to 3 hours on a Sunday when no one's working in the infrastructure is acceptable to provision a whole new set of machines and pass them off. And for the most part, not everybody needs to be Google or Facebook every time you design an application, right? Like you don't need Redis everywhere and like Mongo and, you know, like we use Docker. What's Docker? I don't know, but we use it. Like you can keep things simple and still be pretty effective, but you have to be, you might be limited by the time constraints of how long things happen. And again, you know, this is written by basically sysadmins that know a little bit of Python. So it's constantly evolving. So I'm going to give you some code examples because this is PyCon, and you can feel free to ridicule me after this talk. This is what I would call stupid sysadmin tricks. So this is how we read without a database by basically having methods that check, that do file locking and other stuff. And this is how we sort of force integrity. It's not ideal, but it works. And for the purpose of quads and sort of our time frame for provisioning, it's acceptable. But we should always want to improve things like this. Here's another example: writing data without a database. Like, okay, hold my beer. I'm going to write data without a database. But it works pretty well. We've had some ugly bugs. People have lost some data, but it's in a good state now. But we want to change all of this. So I'm giving you an example of you don't have to have a database for everything. You don't have to, you know, have a crazy amount like memcache and all this other insane stuff to do a simple task. All right, so where are we going to go for this? So we sort of have a Milestone 2.0 where we're going to have, right now we're using simple HTTP server and basically a basic Python WSGI server. We are going to move to Flask. We probably should have moved to Flask originally when we started, but that's neither here nor there. So we're going to move to Flask. This also makes it easier for us to present, you know, sort of a UI to people so they can self-service, schedule their own hardware, and then later down the road it spins up and does their stuff for them. We want to move more towards away from flat files and move to something like SQLite, or maybe support Redis or, you know, MongoDB or something else. Probably SQLite's my choice. And then we want to have Celery on the back end, so we're not doing sequential provisioning. We're not saying, okay, 200 servers, we're going to go down the row and we're going to provision every one of them, then we're going to validate each one, and we're only going to halt if there's an error. We're going to batch all this out to individual processors, have them do their job, have them report back to status. So that's probably a better way to do it. Again, feel free to abuse me after this talk and tell me how I got it wrong. Yeah, so overall, some things you should take away from this, besides Will Foster does not know how to write Python, is that we like simplicity. We basically, our goal was to automate as much as we could, especially the stuff we don't want to do, and do it in a simplistic way that when we add more things to it, it doesn't explode out of control. We wanted to spend more time building a system that builds all the other systems than being in the business of manually doing switch changes, or, you know, maybe you have that templated, but you're still maybe creating new VLANs, or babysitting kickstart processes, or things like that. We wanted to get away from all that, and we wanted to spend the time automating a system that does all of that. I love switches, I love connectivity, but I don't want to do that for a living. Same thing for documentation. It's so important, it's so critical, and what we found is we screw it up, or we forget to update things that are critical. And then lastly, the whole purpose behind this and the, sort of the scale lab within Red Hat is that we wanted to eliminate server hugging and silos of individual hardware that teams might buy at different intervals. So Team A might buy HP servers a year ago, Team B might buy Dell's last year. So all the hardware renewal for the hardware, nothing matches. Nobody knows who knows what. That's expensive. So we with Quads, we're able to share a giant pool of hardware within the engineering areas of Red Hat and then selectively lease and reclaim it to the various groups. So that's sort of the impetus behind that. I'm probably over time. Way over time, okay. Okay, so that's basically it, guys. Thanks for sitting in on my talk. I'm available to answer questions or to take a beating about my Python practices.